Now we get started. Okay. So Jacob will go behind. And have a new person. Okay. So last time we ended with a discussion of eigenvalues. And then I wrote up a 3x3 rotation matrix. And we found the 3 eigenvalues, which it might have been surprising, but even though the rotation matrix was composed of real numbers, 2 of the eigenvalues of the matrix were actually complex. And moreover, we found the eigenvectors, 3 different eigenvectors, and we found that 2 of those were complex as well. So, one of the lessons there is that eigenvalues are the doorway into starting with something that's real, a linear transformation that's real, but you're forced to accept the existence of complex eigenvalues or complex eigenvectors, etc. Okay? Now, that obviously follows the true story that if our linear transformation can be represented by an n by n matrix, then there are n eigenvalues and n eigenvectors, correct? No, that's bullshit, okay? You're never guaranteed to have that many eigenvalues, nor that many eigenvectors, okay? In fact, we have a couple of pieces of terminology. So we have the algebraic multiplicity of an eigenvalue is the number of times I thought it was coming from the computer actually. It is the number of times it appears as a root of the determinant of the linear transformation minus lambda I equals 0. Okay? So this is what we call the algebraic multiplicity of an eigenvalue. And then secondarily, we have what is called the geometric multiplicity. And the geometric multiplicity is the number of linearly independent eigenvectors belonging to an eigenvalue lambda I. Okay? So let me give you an example. Yeah, okay. Actually, no. Yeah, I'll state this afterwards. Okay, so let's imagine we're looking at a linear transformation given by the simple matrix, 2x2 matrix, 1, 0, minus 1, 1. And again, that's me talking, but writing something totally different, which is certainly a malfunction in my brain, but that's the way it goes. Okay, so if we do the determinant to find the roots, which are the eigenvalues, we find that the determinant of A minus lambda I is going to be 1 minus lambda squared. We want to set that to 0. And this, of course, means that the first eigenvalue is 1 and the second eigenvalue is 1. Okay, there are 2 eigenvalues because it's a quadratic. There are 2 solutions, but they happen to be identical. Okay? So, Zan, what's the algebraic multiplicity of the eigenvalue lambda equals 1? It's 2. Good. Yeah, that's some simple questions, aren't they?
That was a good question.
Okay, now let's see what the geometric, no, sorry, that's algebraic, not geometric. Damn. I was writing the wrong words. That's the algebraic. Now let's investigate the geometric. So A, B equals AB. Okay, so we want to find the eigenvector associated with the eigenvalue 1. That's why there's no arbitrary, there's no non-1 coefficient in front of it. A minus A plus B equals AB. How many solutions do I have? Linearly independent solutions, that is.
You should have 2.
I should have 2? What do you think? Let me draw a card. Sarah? Sarah's not here. Okay. Bohanna. How many solutions do we have to this?
5.
Linearly independent ones, that is. What does A need to be?
It needs to be 0.
A needs to be 0. So how many linearly independent solutions? We have 1, exactly. So in this case, the geometric multiplicity equals 1, okay? So this actually feeds into a theorem, which is that the geometric multiplicity of an eigenvalue is less than or equal to the algebraic multiplicity. Okay. Okay, so a linear transformation, does it always have at least 1 eigenvalue?
Yeah.
Why so?
Making the smallest matrix, you can make it a 1 by 1 matrix, and then the eigenvalues will be whatever values in there.
So an n by n matrix, does it always have to have at least 1 eigenvalue where n is arbitrary?
I think you don't probably have 0 eigenvalues.
I can't
I
understand.
don't have no eigenvalues. Because isn't 0 a valid eigenvalue?
0 is a valid eigenvalue.
So it has to have at least 1 linearly independent row or column for it to give you at least 1 eigenvalue.
Yeah. That's okay. So you're thinking about it in slightly more advanced terms. Or you could just say, you know, this equation is always going to be an nth order equation. It's got to have at least 1 solution. It might be repeated numerous times, but there's got to be 1 solution. Okay? All right? And therefore, there has to be at least 1 eigenvector. So every linear transformation is going to have at least 1 eigenvalue and 1 eigenvector trivially. Okay? Whether they have more is really hanging on whether the eigenvalues are going to be different. Okay? Okay. What's the most number of eigenvalues you can have? Distinct eigenvalues? N. Okay, so you're going from 1 up to n eigenvalues for an n by n linear matrix representation of a linear transformation. Okay, now here's yet another theorem. If 2 matrices are similar, that is, A is similar to B if A equals C, B, C inverse, Then they have the same eigenvalues. With the same geometric multiplicity. Now, I don't want to prove this, but I kind of want to give you some hints into the proof of this. So, in order to understand this, let me consider the eigenvector and eigenvalue, or an eigenvector and eigenvalue, associated with the operator B. Okay? So B on a basis vector xi is going to give me an eigenvalue lambda I times the basis vector xi. And now, what we can do is we can apply C inverse, that's this transformation, that is part of the definition of A being similar to B. If I apply C inverse to each side, I have C inverse Bxi is lambda I C inverse xi, because lambda i's are just numbers. Of course, they're going to commute with any transformation. And now I'm going to do that slick thing that mathematicians and theoretical physicists love to do, and that is shove the identity in here in a special form, in which case this now becomes C inverse B C inverse xi, and that is equal to lambda I C inverse xi. I wrote my inverse in the wrong place here. Sorry about that. Now, what is the C inverse BC? On the left, it's just A. C inverse xi equals lambda I C inverse xi. Okay? Well, this is just a different vector. But notice, even though the vectors are different, the eigenvalues are the same. Okay? So your eigenvectors associated with two similar operators, the eigenvectors might be different, but the eigenvalues will be the same. So if you find the set of eigenvalues to one operator, you're guaranteed to have the exact same numerical eigenvalues to any similar operator. Now, even though these eigenvectors are different, okay, the xi's here and the yi's here, if one of them forms a basis for the space, so if you have n eigenvectors, linearly independent eigenvectors in an n-dimensional space, that forms a basis. If one of them forms a basis, the other will form a basis as well. Okay? All right? Okay, now let's actually take it easy for a minute, and let's talk about eigenvectors and eigenvalues and all that garbage in the simplest possible setting. What is the simplest matrix representation of an operator for which finding eigenvalues and finding the eigenvectors is the easiest?
The identity matrix?
The identity? Well, no. I'm not thinking of a specific transformation, but the form of a transformation.
Diagonal matrix?
Yeah, when it's diagonal. Okay? So let's look at the case of a diagonal linear transformation. Let's explore. So, okay. So I'm going to refer to the diagonal matrix as D, and of course it's just got diagonal components and zeros everywhere else. Okay? basically, if you play out the eigenvalue story, then this just reduces to the fact that the eigenvalues of the matrix just correspond to the diagonal components. I'm sure that's something you've heard before, but you can prove it to yourself very quickly by using this defining eigenvalue expression. Okay? Moreover, if we take this story and we look for the eigenvalues, or the eigenvectors, then these are very simply found to be zeros everywhere except for one spot associated with that particular eigenvalues index. Okay? So here this is the 1, 2, 3, 4, I, the 5, 6, da, 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 up to n. Okay? Now, here's an interesting observation. If we take this and we combine the eigenvalues common to both a diagonal matrix, that's this guy, and any similar matrix, so a matrix which is similar to the diagonal, then we have the following. The diagonal is equal to P inverse AP. They're similar, but P in this case is the matrix composed of the eigenvectors of the transformation A. Okay? Man, you guys are so quiet out there. It makes me feel like I'm talking to a brick wall. It's kind of crazy. I'm going to start just asking random questions and picking cards just to wake you up. Joe, what's your favorite color?
Blue.
Blue. Josh.
With Josh.
Mo.
That Josh.
What the hell's your last name?
Just call him Josh too.
Say it again?
Moeller. M-O-L-E-R.
Well, no, it's the O is connected to the L, and then the E is like, the spelling of Mueller in here looks really weird. Okay, Josh. What's your favorite animal?
I like squirrels.
Josh.
Yes.
Honestly. What's your favorite? That's a question.
That's a tricky one.
Answer it, damn it.
Yes.
Yes, okay. That is perfecto. Sorry, you guys, you're so quiet. It's like it's no interaction. I'm not interacting with you at all. Okay, yeah, no, I know it's hard. We have to socially distance ourselves. That means no communication, no laughing. Cover your faces. Okay, anyway. All right. Okay. Now, notice for a diagonal matrix, so not everything can be brought in terms of a diagonal matrix, okay? But if you can bring things in terms of a diagonal matrix, how many linearly independent eigenvectors will you have? Yeah, you'll have n linearly independent eigenvectors. But that, of course, means that any similar transformation is also going to have n linearly independent eigenvectors. And they'll share eigenvalues, okay? So, one way to find the diagonal form of a matrix is if I give you the matrix A corresponding to some linear transformation, then you find the eigenvectors of A. and hoping that they form a complete basis, you then just form the matrix P, whose columns or rows are composed of the eigenvectors. You form P inverse, and then you do this multiplication, and you get the diagonal representation of A. Okay. That's kind of silly because in order to find the eigenvectors of A, what do you have to know about A? The eigenvalues, which are what's going to pop up here. So it's kind of silly, but in principle it's a definition. There's more practical ways that you would approach actually diagonalizing a matrix. Okay? And hopefully, well, maybe it would be relevant for me to tell you later on, but hopefully you realize that the diagonalization of a matrix dramatically simplifies its role in algebraic equations. Okay, so let's go back to an example real quick to see how this is fleshed out. So you might remember from our last lecture, I did a rotation in the xy plane represented by a 3 by 3 matrix, and we found the eigenvector, or the eigenvalue 1, and a eigenvector associated with that, which just pointed in the z direction. That was the intuitive eigenvector of a rotation in the xy plane. If you've got a vector pointing in z and you rotate in the xy plane, it clearly doesn't do anything to z, so the eigenvalue is 1 and the vector just has a z component. Okay, and then we also found these more complex versions, e to the I theta, with an eigenvector a minus ia 0, and lambda 3 e to the minus I theta, with an eigenvector minus ib b0. Okay, so this was the complex interlude into what was otherwise a real story, but nonetheless, these eigenvalues and these eigenvectors certainly work out for the rotation of the xy plane. Okay? Now let's do it. Let's form the matrix composed of the eigenvectors. So we're going to have 0, 0, c, a minus ia, 0, minus ib, b0. Okay? And now using this, we can apply P inverse AP. Okay? You can do the 3D matrix multiplication, but what do you think this is going to end up giving me? What if I take the transpose of this, or sorry, the inverse of this, multiply A, well here, I'll just show you because I guess the inverse is not obvious. So the inverse of this is 1 over the determinant. The determinant happens to be 2abc. Okay, so that's the inverse of this matrix. And then we want to hit our original rotation matrix with this. And then multiply by P. Oh, it's a heart, but it needs to be a 0. Don't laugh. I'm doing the best I can, writing rapidly, because I've got so much to write. Okay, now you want to multiply it out in your head? Okay. No, we don't want to. It's diagonal e to the I theta, e to the minus I theta. Okay? Does it seem like it worked? But it sure as hell does. Okay? All right. So, let me think. Let's see. So, One more quick observation. What is the determinant of D, the big diagonal matrix D? Yeah, it's the product over all the eigenvalues. So that D is just a product over the eigenvalues, which is, of course, the same as the determinant of A, because it shares the same set of eigenvalues. Now remember, this diagonalization requires that A have a set of eigenvectors which span the space. We could imagine, though, trying to do this with a matrix of the following form, 1A, 0, 1, in which case we have AXI equals lambda I xi, 1A, 0, 1, BC equals B plus AC over C, and we want that to be an eigenvector. So we want it to be some constant times the first vector. And this only has the solution. X1 is B0 with the eigenvalue 1. And so the eigenvectors do not span the space in this case. Okay? So there's no way that you could diagonalize this matrix A through some similarity transformation. Okay? All right. Now I'm going to give you one more result, and then we're going to turn the page and look at new stuff. Okay, so one more interesting theorem. If the determinant of A equals 0, and the eigenvectors of A span the space V on which A acts, then the expression AX equals B has a solution only if B is a linear combination of eigenvectors for which the eigenvalues do not equal 0. Okay? That is, of course, a theorem that needs to be proved, but we're just going to look at through an example. So if I take my matrix to be just a diagonal matrix, okay, then there's no mystery as to what the eigenvalues are. Okay? And also the associated eigenvectors. Okay? And clearly, these three eigenvectors span the space. We on board with that? I mean, what space is this thing acting in? If everything's real. It's acting in R3. Okay? So it's acting in R3. We have 3 basis vectors in R3. Okay? Now, given B in this expression as kx2 plus jx3, where k and j are just some constants, then we can solve. Ax equals b. Which gives us that x has to be kx2 plus 1/2 jx3. Okay, stare at that for a moment. Hopefully it's obvious. Are we good? Does anybody want me to flesh this out? Raise your hand. Okay, that's fine. That's fine.
Wait, nope, I got it. I
Okay.
get it. I get it. Yep,
Okay.
I think so.
So notice B is a linear combination
Sorry.
of eigenvectors which do not have 0 as an eigenvalue. Okay? If, however, I take B to be a constant, non-zero constant times x1 plus a linear combination of the rest of the eigenvectors, then this has no solution. I want you to stare at that for a moment. Does this make sense? Or do you want me to fill in the details? Yes or no?
Yeah, fill in the details.
Fill in the details? Okay. So AX, so X is going to be some linear combination of the basis vectors. Any vector can be expressed as a linear combination of the basis vectors. So we'll say alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3. And I want that to be equal to hx1 plus kx2 plus jx3. Okay? Now, if I think about what alpha 1 x1, oh, it's just alpha 1 times a. So that's going to be alpha 1a, 0, 0. A acting on it, plus A acting on 0, alpha 2B, 0, plus A acting on 0, 0, alpha 3C. And I want that to be H, 0, 0, HA, 0, 0, plus 0, KB, 0, plus 0, 0, JC. Right? Okay. Well, A acting on this second constant times the eigenvector is just going to give me the eigenvector. A acting on this constant times the third eigenvector is going to give me 2 times the eigenvector. But what is A acting on the first eigenvector going to give me? 0. Okay? So there's no way to reproduce this term. All right? And H and A are considered non-zero. Okay, so there's no solution. All right? Okay, are y'all about ready to be done? Move on, introduce some inner products.
I have a question.
Yeah, go for it.
Why is x1 a 0, 0 and the same for x2 and x3. Like,
Sorry, say it again?
why is x1 equal to a, the column vector a0, 0? Why is that general?
So I want A on A, B, C equals to 0 times A, B, C. The eigenvalue is 0. I mean, if you do the, so the eigenvalues of this are obviously 0, 1, and 2, right?
Yeah.
Okay? So if A on ABC is the number 0 times ABC, then what is the form of, so literally, this is our matrix.
Right.
Okay, so can B and C be anything? Non-zero? No, they have to be 0, so that only leaves A. But A is flexible,
Oh, okay.
okay?
Okay.
Make sense?
Yeah, it's coming around.
I just feel the need to confirm the B in ABC is different than the B equals KX2 plus KX3.
Sorry, the B,
The B's are different, right? Just gotta,
the B's in these two examples?
no, in the ABC vector.
Oh, yeah, sorry, yeah, they're different, sorry. Yeah, I mean, there's just too damn many unknowns. I need to go Greek, I need to go Finnish, I need to go Japanese with my index notation. Oh, no, just kidding. All right, any other questions? Okay, all right. Let's get some inner products on the board. So we have parade through the definitions of vector spaces, and we have parade through almost all, but pretty much all of the information that can be gleaned from a vector space without ever denoting several things, without ever denoting what the hell the length of a vector is. We've never used the length of a vector in anything we've talked about. We've never used the angles between vectors. Okay? Largely because we've never used a product of two vectors, which gives you another vector, or which gives you something, a scalar, it turns out, okay, for inner products. So, now remember, I want you to remember, before I introduce the inner product, that we did see something which looked suspicious, where we said this product of operators gives me another operator. But this has nothing to do with an inner product, okay? Remember, Bx is a linear transformation of a vector x. So what it does is it gives me back a vector y, and then I act on y with the linear transformation A, okay? So even though we're multiplying linear transformations together, this does not imply any product of vectors. But now we're going to introduce that. So what I'm going to do is, as usual, because we're going the mathy route, instead of talking about the dot product, which is certainly an example of an inner product, instead of talking about the dot product and then trying to generalize it, I'm going to hand you the most general definition of an inner product, and then we'll talk about examples. But the most general definition of an inner product might seem a little bit softer than what you're used to. Okay? So let's get it down. An inner product in a real or complex valued vector space is a scalar valued function of the ordered pair. And that might already alarm things. Ordered pair? What? Of vectors x and y such that the following three conditions hold. The inner product of x and y, which will be notated by brackets around them, must be equal to the inner product of y and x complex conjugated. Okay? Note, if they are real, then order doesn't matter. Okay? Because if they're real, complex conjugation doesn't do anything. So in the real case, xy is equivalent to yx. Okay? But if they're complex, then reversing the order affects a complex conjugation. And the complex conjugation of a complex number is a different number. Okay? Everybody's looking out the door. Who's out there? Okay. I'm just checking. I'm just checking. Okay, number 2. If we take, now these might be a little bit more expected. If we take linear sum of vectors and we do the inner product with a third vector, then this is going to give me alpha star xz plus beta star yz with alpha and beta scalars. And then 3, if I take the inner product of a vector with itself, this is going to be greater than or equal to 0 for any x. And the corollary of that is that if the inner product of x with itself is 0, then that implies that x is the 0th element. Okay? This is called positive definiteness for the inner product, and it is something which can be relaxed. We're not going to relax it right now, but can anybody tell me a context in which this requirement of the inner product is relaxed? All right, I'll ask somebody. Anna.
So we're looking for where we don't necessarily need to fill number 3.
Yes. Or where we don't.
Is there, because wouldn't the inner product of x with itself basically give you the square of the length?
Yes.
So how would you end up having the square of the length be 0 if the length wasn't 0?
That's an interesting question.
Because I don't have the answer. I know what you're asking for, but I definitely don't know the answer.
You want to phone a friend?
Yes,
You got
I
2
definitely
people with their hot hands up.
Complex?
Complex?
Complex vectors?
Nope, complex vectors. No, this is gonna, we're gonna talk about that in a minute, but no, complex vectors are always gonna have greater than 0 inner products. Yes?
Well, she was saying, if the length is greater than 0, then the square of the length is going to be greater than 0. But then you said complex and it's still not that, so I don't know. I was thinking that symbol was greater than 0, but I now see it's greater than equal to 0.
What
Yeah.
if its length is less than 0?
Well, square.
Yeah, so in what context do you encounter an inner product that has values less than 0? Anybody encountered one?
Sometimes they occur in special relativity when you're dealing with space-like intervals.
There you go, Ross. Yes, in special relativity. In special relativity, I can give you a vector, which is the displacement in the t direction and in the spatial directions. And the inner product of this with itself can be plus, minus, or it can be 0. We will go through some special relativity later, but this is messed up because not only do you find that the inner product, which is defined in this context, give you magnitudes of vectors squared, which are negative, it also gives you that the magnitude of a vector squared can be 0, even though that's not the 0 vector. It's pretty crazy stuff. If you're really curious about all that, take my general relativity course next semester and we'll beat the crap out of it. But I'll mention some of it
Alex.
later. Yes?
So is this more generally like if you're in non-Euclidean space, it could be negative?
Yes.
Okay.
Yes. Okay. All right. So this is our definition of an inner product. And let me give you some more vocabulary. If the vector space is real, then this means that you are dealing with what is often referred to as a Euclidean inner product. Okay? Whereas if the vector space is complex, then you are dealing with what is called a unitary space. And this can be a Euclidean space with a Euclidean inner product. Okay. So I just give you this because occasionally I'll say Euclidean, occasionally I'll say unitary, and that's just code for real versus complex. Okay? Now, with this in hand, with this general definition in hand, we can draw some interesting conclusions. First of all, we can define the length of a vector as the inner product of the vector with itself times 1 over root 2. Okay? And this is part of the reason for the star here. Okay? Because if I'm taking x with x, if I'm taking the inner product of x with x, and by the way, I haven't told you what the inner product looks like yet. This is the general definition. We'll go through some examples in a moment. But a general inner product just has to satisfy these requirements. Okay? So if I'm taking the inner product of x with x, well, hold on. Okay, so if I take the inner product of x with x, and I just call this 1 and 2, just to give them different names, you know? How is that related to the inner product of x with x, where that's 2 and 1? Well, no. They have to satisfy this. Yeah, so what's the inner product of a vector with itself? It's always real. Okay? So the inner products of, or the lengths of vectors are always real, even if the vector is complex. Okay? So that's one definition. We can also use the inner product to define the angle between two vectors. Okay? And this holds in any number of dimensions. Now you might be like, well, wait a minute, you know, if you're 4 dimensions and you've got 2 vectors, they might be, well, remember, if you have 2 vectors in 4 dimensions, 2 vectors, 4 dimensions, 6 dimensions, 12 dimensions, it doesn't matter. 2 vectors form a plane. Okay, and you can define a spherical polar coordinate system up to n dimensions, but given a plane, you can define the angle theta in that plane and talk about the angle between the 2 vectors. It doesn't matter what dimensionality you're in, okay? So we've got the angle between 2 vectors. And then, of course, this immediately tells us how to define the most important property of orthogonality. That is, if the inner product of two vectors gives you 0, then x and y are orthogonal, which of course is also by definition that the angle is 90. Okay? And then this, of course, is last but not least, leads us to the notion that the set x1, x2, xn is orthonormal if the inner product of xi with xj is equal to delta ij for any I and j. Okay? Where the result of the inner product is, of course, the delta function, which is 0 or 1, depending on whether the indices are the same or different. Well, different or the same. I said 0, 1, different or the same. Okay? And clearly, if we have a definition of the length of a vector, then we can obviously define a unit vector, a vector of length 1, which points in the same direction, okay, as the starting point vector, but has magnitude of 0, or length of 0, or sorry, a length of 1. Well, okay? All right. So, yeah, so let me finish up with some examples of inner products. And when we come back next time, we'll start investigating some of the things that we investigated for vector spaces, but utilizing the inner product, which in many cases eases things. Okay, so,
Wait, Ron,
yeah.
is the magnitude the inner product of 1 over root 2?
Oh, sorry, that's, yeah. Whew. It's 1/2.
Thank you.
My apologies. Sorry, well, you guys should have pointed that out much earlier. I actually put that root up there intentionally, hoping to goad you into correcting me, but you're all like, he's so smart. That root's got to be there. I have no idea where the F that came from, but wow.
I just did the Pythagorean theorem like 10 times.
Okay, occasionally I just write the wrong thing up there, so. Yeah. And I honestly, I did that before this, so it's a history of mine to write the wrong thing on the board. Okay, all right. Yeah, so let's look at some examples. And I know I'm erasing all of the defining properties of inner products, but hopefully you've written them down and you can refer to what you've written or what you're looking at in the course notes, which you've looked at from the web page. Okay, so some examples. For Rn, that is, if you're dealing with a Euclidean vector space, this is the good old dot product. And we all know how this goes. If I have a vector with components AB, a vector with components CD, where these are the matrix representations of the vectors, okay, then the inner product is, of course, AC plus BD, which is, of course, the same as the inner product of YX. Yeah?
Are you using bracket notation?
I'm using a bracket notation.
Oh, okay, thanks.
Okay? So Cn, this is a bracket. I mean, this is always going to be a bracket which is bilinear in two vectors. So yeah, I mean, these are brackets as well, but these are just the brackets that surround the matrix.
Are they parentheses or?
Well, that's the thing. So I want to align with what the book is doing, and what the book is doing. Hold on. I want to be honest and faithful. No, hold on a second. So, yes, at every point in the book,
Okay.
that is the notation. It's not this.
Yeah. Okay.
Yeah, and I just want to match what's in the book.
That's fine.
Okay, that's all I'm trying to do. But I wanted to look over the book just to make sure that there wasn't like a little bit of an acute arch, but still smooth. But no, it's just a frickin' parenthesis. Okay? Nothing I can do about it. That's the book you're dealing with. What do I do with mine? Oh, there we go. Good. All right. So for Cn, this is almost the same. For Cn, if we have x is a, b, and y is c, d, then x, y comes out to a star c plus b star d. Okay? Now you might be like, wait a minute, hold on, pause. Why are you only starring the first one? Well, you only star one of them. And the definition can be cast on the first of them, but it doesn't matter because this is what you need in order to satisfy that requirement. Okay, everybody see that? Okay, good. Now, in both of these cases, I'm doing this in terms of the components, but there is an underlying assumption that the length of the basis vectors you are using when you do it this way, that the length of the basis vectors is 1. Okay? That is not required. So, for example, I mean, in order to do this in full gory detail, what we could say is that in real space, x is a I hat plus b j hat. These are the basis vectors having magnitude of 1. And then y is c I hat plus d j hat. And then, obviously, xy is a c I hat dot I hat plus a d I hat dot j hat plus b c j hat dot I hat plus BD j hat dot j hat, which just gives me AC plus BD. Okay? However, sometimes we won't do that. So sometimes we might say the following. If the components of x are AB and the components of y are CD, and we're talking about a vector space over R, so this is Euclidean, then we can define the inner product of x and y to be AB matrix multiplied by CD, where in this case, what matrix did we use here? The identity. But we don't necessarily have to use the identity. We might use this. Okay? Right? All this is doing is it's saying that the length of the second basis vector is actually root 2. Okay? So you don't have to work with basis vectors which are all length 1. You can work with them of any length you want, but it's going to change in a critical way how you define the inner product. All right, we on board? Yes?
Do x and y have to be in the same basis?
Do x and y have to be?
In the same basis.
Yes. Yes. Okay? Yeah, so taking a vector from one basis and multiplying it by a vector in another basis, what does that mean? Right. So the inner product is something which is defined. It's actually defined in a vector space. Not necessarily with basis vectors, but usually in terms of basis vectors. Okay, we'll talk about that in a minute. But it's defined in terms of one representation. So if you choose a basis, then your inner product is between vectors represented in that basis. Okay? All right, so a couple more examples and then we'll get the hell out of here. We could work in the context of a non-orthogonal basis. Okay, so imagine if I started with a basis vector u1 and then I considered another basis vector u2 and they had a 45-degree angle between them. Are these linearly independent? Yes, they are. Yeah, so remember, back when I introduced vectors and I had not even mentioned the inner product, there was no mention of what orthogonal meant. I said vector spaces can be spanned by linearly independent sets of vectors, where linearly independent means that no vector can be written as a linear combination of the other vectors. So we could pick a non-orthogonal but linearly independent set of basis vectors, and then we can talk about the inner product. So if x is AU1 plus B U2, where this is the U1 vector, this is the U2 basis vector, and y is CU1 plus DU2, then the Euclidean inner product gives me AC U1 plus AD U1 U2 plus BC U2 U1 plus BD U2 U2, where all four terms contribute. Because clearly the inner product of U1 and U2 is not zero, they're not orthogonal. Okay. Obviously, it makes sense to use an orthogonal basis. Okay, but maybe you start out and you're not using an orthogonal basis. Okay, so sorry for carrying over, but I want to finish up these examples and then we'll get out of here. So, well, wait, when would you ever be dumb enough to do this?
Solid state.
Okay, well, I'll give you an example in just a second. Okay? But before I get to the example, there's something else I want to talk about. So consider a vector space we've played with a ton of times. The simplest case of it, P1, well, P0 is pretty simple, but P1, where this is expressions linear in the variable t, okay? And we're going to take t to be on the interval from 0 to 1. And then we've got two vectors in this space. Now, we might consider that x and y is just alpha 0, b0 plus alpha 1, b1, or beta, sorry, alpha, beta, okay? But that's kind of ignoring the t's. And remember, there is a sense in which we're working with a set of basis vectors which are given by 1 and t. So this story here is not using at all the length of the basis vectors, but how the hell do you define the length of the basis vectors? And for that matter, how do you know if these are orthogonal or not? Okay? So this is not going to be a sufficient means of defining the inner product. Rather, what we will use is the following. X, inner product with y, is given by the integral from 0 to 1 of x star x star y dt, where both x star and y are both functions of t. All right? Clearly, this integration over t is going to take care of this functional dependence. And so x inner product with y ends up being alpha 0, beta 0, plus 1 half alpha 0, beta 1, plus 1 half alpha 1, beta 0, plus 1/3 alpha 1, beta 1. And literally, if you just take this, complex conjugate it, multiply it by this, integrate it, you'll get this. We won't complex conjugate that because we'll assume it's real. Okay? Now, here's a question. I mean, I'm looking at it and I'm thinking, this is way more like this than like this. So what are you thinking about 1 and t as basis vectors? You think they're orthogonal? They're not. Okay? I mean, hell, if we take 1 and we take its inner product with t, if we just take the basis vectors alone with coefficients 1, and we take the inner product, we get 1/2. They're not orthogonal. Okay? You might have been thinking, oh man, 1t, or 1t, t squared, t cubed, t3. He's using an orthogonal basis. No, I wasn't. I was using a linearly independent basis, but not an orthogonal one. Do we have an orthogonal basis that we can use when we're dealing with these frickin' polynomials? Yes, we do. What is the orthogonal basis?
1 minus t, 1 plus t.
Oh,
Square root.
of
But it gets better because instead of this, we can use 1 plus root 3t over 2 plus root 3.
Why didn't I think of that?
Oh, sorry.
Congratulations. Oh, is that really normal?
No, these are just sets. I'm not taking it. Yeah. So this is an orthogonal basis. This is an orthonormal basis. Okay? It's not obvious, but take the inner product. Okay, and you'll get 0. Take the inner product of one of these with itself, and you'll get 1. Okay? We on board?
Did you say one of them was orthogonal and one is orthogonal?
So these are just orthogonal.
Okay.
If you take these and you plug them in here,
Yeah.
you'll get 0. If you take one of them and you do the inner product with itself, you'll get something which is not 1.
Oh,
So to normalize them, you divide by their magnitudes.
gotcha.
That's all I'm doing.
Yeah.
Okay? Okay. There are other definitions for inner products. For example, here, this is an inner product of a function. And we can imagine other functions other than just polynomials. You could relax this into the integral over some other interval from a to b. Okay. Of course, your functions have to be well defined over the entirety of the interval that you're using in the definition of the inner product. You can also use a weighting function. That is, instead of just taking x and y and doing the inner product of x times, or taking the integral of xy, you can define this with a weighting function. Okay? So if you're taking the inner product of x and y, then you plug x and y in here, but every inner product that you do is accompanied by this weighting function. Okay? Okay, so this is just a generalization of the inner product. But all of these inner product examples satisfy the three defining characteristics of an inner product. Okay? All right, more next time. Let's get out of here. Hi, folks. Any questions?
That was good. Thank you, Alex.
You're welcome. All right, see ya.
Don't do me like that.
Oh, thank you. Bye, Russ.
Oh, have fun with that, man. I will.
Apparently my PA class is I don't understand why we
PA is still happening this semester?
It's all online.